All right, we're going to introduce some cool properties, and this should be a useful section. I think it's kind of fun to really kind of show the mathematical thought process that goes behind the scenes when people are creating these things and working with them for the first time before we have theorems. So remember, again, we haven't shown you why this is useful yet, and we're going to get there eventually, I promise. But this is useful because I said it's going to turn derivatives in algebra. This is my promise to you. This is would be wonderful, right? To turn derivatives in algebra. And let's see if that's actually true. And we're going to see it through an example. And the reason why I say that this is useful, like to show mathematical thought process, again, we're going to find the Laplace transform on the derivative of a function. Instead of just a regular function, how does it work on its derivative? And because this is really the kind of questions that people ask. They say, okay, let's come up with this so that it might get rid of derivatives. Then, okay, well, what is the Laplace transform of a derivative? Do they cancel each other out? I know derivatives and integrals kind of cancel each other out. If they don't cancel each other out, are they close? And if so, like, what are the numbers? And they just play around with it. So that's what we're going to do. We're going to play around with this and see if it's something useful. It probably is something useful, or else I probably wouldn't waste your time in this video with it. But I want to show you that, like, the people who did this, they don't know. They have guesses, and they want to see how it works. So they play around and they solve a problem. So let's do that. So what is this Laplace transform? That's going to be the integral from 0 to infinity of our function, which in this case is dy dt, and it's a function of t. All right, multiplied by e to the negative st dt. How do we do this integral? Well, we can't. Not like this anyway. Right? You can't just take the integral of two things individually, right? Just like you can't take the derivative of two things individually if they're multiplied. If they were added, yeah, we could split it up. But if they're multiplied, we have to undo the product rule somehow. Integration by parts. So in integration by parts, we have two things that we see here, and we have to choose one of these to differentiate and one of these to integrate. Do we want to differentiate this derivative? No. Do we want to integrate this derivative? That would be great. Okay, so what we're going to choose is we're going to say let u be e to the negative st, and we're going to say dv is dy dt times dt. Oh, this is a really nice thing to integrate. What's the antiderivative of dy dt with respect to t? It's just y. Nice. And then what is du? That's going to be negative s e to the negative st. So then what we get, we have a definite, before we even evaluate integration by parts, we're going to need a limit. I hate improper integrals, but we're going to be good. The limit as b goes to infinity of this from 0 to b. Here, I really will be good, right? This is dy dt e to the negative st dt. And what that is the limit as b goes to infinity, integration by parts. U times v, which is going to be y e to the negative st, evaluated from 0 to b, minus the integral of v du, which is minus a negative will be plus integral from 0 to b, v du. So this is going to be, well, the s can really come out in front. I didn't really leave room for it. I don't like that. The s could come in front. S times y e to the negative st dt. All right, so let's move this to the other page so that we have a little bit more room to write. And let's look at this, because this doesn't look great. But it's not too bad. Because what we have right here is, what is this first thing? Again, let's keep the limit. That's going to be useful. We plug in b. What are we plugging b into? T. So this is y e to the negative s times b minus, when we plug in 0, the exponential becomes 1. Just turns out to be plugging in, ooh, we have to be very careful here. We have to be very, very careful here. Y is a function of t. Okay. So we should really be looking at, this is y of b e to the negative sb, because this is a function y of t. So we're not plugging it, like we're plugging in everywhere that has a t. There is a t here. This is a function y of t. Similar, that's why we couldn't just factor out a y here. Okay, because y depends on t. It can't come out. It's not a constant. And we plug in 0, the exponential becomes 1, and we're just left with y of 0, like so. And now this second integral doesn't look great. Do we use integration by parts again? Do we use a substitution? What are we going to do? Well, we're not going to do the integral. We're not going to do the integral at all because we notice that it's basically the Laplace transform. Right? If you distribute this limit, which you can do as long as the limit exists, does the limit exist? Sometimes. Well, we're only going to look at when the limit exists anyway. So if we do that, and again, we can do that as long as the limit exists, and we're only looking at the ones where the limit exists anyway, then we're going to have the limit. This will actually just become integral from 0 to infinity times s, y e to the negative st dt, which is just the Laplace transform. Right? This is the Laplace transform on y times s. So great. So this is just the Laplace transform on y, which means we had the Laplace transform on the derivative, and now we just have the Laplace transform on y, which is much nicer. This is just a constant, our initial condition. What is this? I'm not quite sure. This is where that assumption that we made before is really, really important. The assumption we made before is that our function y cannot grow faster than an exponential function. I don't care how fast y grows, there needs to be some value of s so that this goes to 0. Okay, so again, let's say out to the side, right? Y grows no faster than an exponential function. So what that tells us is that there exists, that's what the backwards e means, there exists an s, so that y of b e to the negative sb goes to 0 as s goes to infinity. Sorry, as b goes to infinity. That's really why we had that requirement. So there will be some s, and we don't necessarily know what that s is. It just needs to exist. Because if there's no s that makes this converge, then we're wasting our time. Okay? So we don't need to know what s is. We just need to know that there has to be some s for which is the case. So this will go to 0 for some s. And what are we left with? Negative y of 0 plus s times the Laplace transform on y. And then this is going to be true for some s big enough. Okay. What did we just show? We just proved a theorem with a little hand waving. To really prove this, you'd want to be a little bit more precise about this. So let's introduce that theorem really quickly. We already did the hard stuff. And that says for a function, y of t, that again grows no faster. We do need this applied to our function. For such a function, y of t, then the Laplace transform of its derivative, I'm trying to use the notation in my notes, but I can't find it. The Laplace transform of the derivative, dy dt, is just s times the Laplace transform on the original function y minus y of 0. So we finally see how this can apply to differential equations. The Laplace transform of a derivative gets rid of the derivative, which is really cool. And yeah, we're off by a constant, and we're scaled by some letter s, which we'll deal with. We'll talk about what that s is later. But we can get rid of derivatives, which is great. Because you can imagine, if I had some kind of differential equation, y prime or y dot or dy dt, however you want to write it, right, is maybe like 3y plus 5, we can take the Laplace transform of both sides. Right, you can square both sides, add 5 to both sides, square root both sides. You can take the Laplace transform of both sides. And then we'll have no more derivatives, which is very cool. But what if we go back to our harmonic oscillator? Oh my gosh, it's been too long. I can't remember the formula. What if we go back to our harmonic oscillator? Can we still Laplace transform both sides? Because if you Laplace transform the left-hand side, you have to do it to the whole left-hand side. Just like square roots and squaring things. So we're maybe in a pickle here. Because think back to exponential functions, right? We know that logarithms undo exponential functions. So if we had an equation like this, we would like to be able to log both sides. But the logarithmic function is not linear. There's no way to split up and simplify this left-hand side. If it were linear, we'd be able to do, oh, this is just 2x, it cancels. This is just 3x, it cancels. But it's not linear. This can't be simplified. This is a mess. If the Laplace transform's linear, then we can factor out constants and separate it across addition. Multiplication's linear, for example, we distribute. And we can factor things out. The square root is not linear. It causes problems. Rational functions are not linear. Quadratic functions are not linear. Lines are linear. All right, so a lot of the things that we know aren't linear, which is a bummer. But maybe the Laplace transform is linear. So that would make things a lot nicer, because here the Laplace transform can do some stuff. But what if we had higher order linear differential equation with constant coefficients? Can we do anything? So just like before, we're going to try to find out. And to do that, we're going to look at the Laplace transform being applied to a constant times a function plus some other constant times some other function. So a and b are going to be real numbers here, and f and g are going to be functions. And just like we say a and b are in R, there is a set that we could name this. But we won't talk about what different kinds of sets contain functions. You can think about it. Anyway, so let's find the Laplace transform applied to a linear combination of these two functions. And we're hoping that we can factor out the constants and that we can add the functions together. That's what we're hoping. Well, what is it? It's going to be the integral from 0 to infinity of the thing we're applying it to, which is a times f of t. I'm going to be very specific that this is a function this time, plus b times g of t times e to the negative st dt. Oh, this is great. This is great because we know integrals are linear. Integrals are linear operators. If you have a constant times a integrand, you can factor out the constant. If your integrand is two functions added to each other, yeah, it's just the integral of the two things added to each other. So with just some quick algebra, right, if we distribute all this, right, we can get a f of t times e to the negative st plus b g of t e to the negative st, and that's all dt. Right, we can see we can split this up into two different integrals. We can factor out a constant. And that works as long as, you know, both integrals converge. So there are some assumptions being done here. But yeah, we get a times the integral from 0 to infinity of f of t e to the negative st dt plus b times the integral from 0 to infinity of g of t e to the negative st dt, which is wonderful because what is this? This is the Laplace transform applied to f. So it's a times L of f plus b times L of g, which is fantastic. So if we did have a second order equation and we applied the Laplace transform to both sides, that really is just m times L of y double dot plus b times L of y dot plus k times L of y, and we can just apply it to each of the functions individually because we have a linear operator here. which is extremely powerful. There's like a whole subset of math devoted to linear operators. They make us all very happy as mathematicians whenever something's linear, because again, nonlinear things are harder than linear things, and we like easy things. Well, sometimes we like challenges too. So we'll close this video with a theorem that summarizes exactly what we talked about. Okay, so for A and B, constants, and F and G, functions, we know that the Laplace operator is linear, which says that L of AF plus BG I play too many video games. These are all funny abbreviations. Is equal to A times L of F plus B times L of G. Okay, in other words, the Laplace transform is linear, is a linear operator. Remember, we said it was a integral operator. I think those are the words that we used. Integral transform, I mentioned it was an integral operator, and that operators are kind of more generic functions that's used in higher level math. Operators can apply to functions. Operators can really apply to kind of any object that we want, but we kind of think of them as functions. In this case, it's like sort of a function on functions, which is also known as a functional. And again, I'm speaking in very broad strokes and being a little bit casual with my definitions, but that is one of the ways to kind of think about these more complicated terms that we're introducing. So this is really nice. Coupling these two theorems, that the Laplace transform is linear, which means we can do things individually, and the Laplace transform gets rid of derivatives, we are finally to the point where we can use this to solve a differential equation. And we'll do that in the next video. Bye-bye.